Hi everyone, my name is Dwight Louie. I'm the Director of Product Development here at IBASE, and we're here today to talk about the SE-92, an extreme environment system for digital signage. When we talk about extreme environments, what we are really talking about is deployments that are actually outdoors or on vehicles, right? And the challenges of outdoor deployments are many. You have to deal with extreme temperature ranges, you have to deal with unstable power sources, and most of the time it's preferable if the solution is fanless, so you do not have airflow contamination. In addition, if you're trying to do a system that not only goes outside but goes on a vehicle that goes around, that moves around, then one of the key aspects of doing that is that you have to have some kind of a power management system that's aware of the state of the ignition of the vehicle, because if you do not have that, you really have no, you have no practical way of deploying a system on a vehicle successfully. Obviously, it being on a vehicle, you need to be shock and vibration hardened, and preferably you also need to be aware of the location of the vehicle and be able to communicate with the device that is not in a terrestrial location where you can actually run a network cable up to the system. So these are considerable challenges, and these are environments whereby a typical PC, a typical desktop computer or laptop computer typically will not function well, if at all, within. So we tackle the problem by building a system that is specialized in going into this kind of environments. The first thing that we did was that we have to design a system that can take very, very cold temperatures to very, very hot temperatures. In the northern hemisphere, in upper latitudes, the system has to survive winter conditions, perhaps in an enclosed environmental box that sits outdoors. It is sheltered from the rain, is sheltered from snow, is sheltered from direct exposure to moisture, if you will. But typically these boxes are not air conditioned. So in the depth of winter, the system has to be able to start up and function at very low temperatures. We design our system to be able to function at minus 40 degrees Celsius, which also happens to be minus 40 degrees Fahrenheit. The system is designed such that it will start up at that temperature, in part because we select only components that will have a wide operating temperature range that is, designed to start up at those temperature, but also because we have a hardware design that has an integral self-heating circuitry. So basically what happens is that when the system starts up, some components will be so cold that they do not want to behave themselves, and wouldn't allow the system to start up successfully. However, once current is applied to these components and to the rest of the circuit, the components themselves will self-heat, and the rest of the circuitry will produce some amount of heat. And usually after a few minutes, sometimes as long as 10 or 15 minutes, the system will heat up sufficiently that it can actually boot. The problem, however, is that most computers will never get to that point. When it fails to start up the first time, it gets stuck in limbo, and unless somebody goes out there and actually presses the button so that it tries to start up again, it's going to be stuck in that state. So what we have is a circuitry that decides that if it's really, really cold, it will apply power to the component, attempt a startup, and if it's not successful, continue the application of power and periodically try again. And in this way, we're able to have the system start up successfully every time at temperatures down to minus 40 degrees Celsius, which is below the operating thresholds of some of the components that we have to employ, given that this is a PC type device. On the other end of the spectrum, if you go out to the Death Valley Desert or the Sonora Desert, or places like that, you'll notice that in summer, temperatures can go scorching hot. It's not unusual to see 120 degrees Fahrenheit or temperatures close to 50 degrees Celsius in this sort of an environment. In that kind of environment, in a box, even if it is sheltered from the sun, the fact that the exterior of the box is exposed to solar radiation, you might see temperatures inside the box in excess of 60 or sometimes even 70 degrees Celsius. So what we have here is that we've employed a very low wattage, a very power efficient processor that only puts out 15 watts of heat. On the other hand, we have a heatsink on there that really in a normal indoor environment would have been big enough to dissipate about 4 to 5 times as much heat. And that allows us to hit temperature maximums of about 75 degrees Celsius. In fact, we tested up to 80 degrees Celsius and function without fail. Now, just cooling the processor itself would not have been enough, even though we have a huge heatsink for that purpose. What we do also is that there are some components that also puts up a significant amount of heat, even if it may be half a watt or watt or so. If you do not cool them, they overheat and they fail. And the system is only as good as its weakest link. So what we do is that we also conductively cool, for instance, the solid state disk. We also conductively cool the network controller chips and various components on the board. We conduct the heat from these components to the heatsink of the system, and that allows us to heat 75 degrees Celsius or about 167 degrees Fahrenheit on the upper end. So what we have then is a system that will operate without fail at very, very low temperatures of minus 40 degrees Celsius all the way up to scorching hot temperatures of 75 degrees Celsius. Now, if that is all that is needed to operate a device in a vehicle environment, that would have been easy actually. But it turns out that if you take that device, and vehicles do get parked outside and they do get very cold and they do get very hot, but just having that wide temperature range itself is not sufficient to operate a device successfully in a transportation environment. And the reason is that we have two additional major problems. The first is that even though cars have a battery that's nominally 12 volts and some heavy vehicles have a 24 volt power system, if you hook the computer up to a power source like this, like the vehicle's battery, you actually never really see 12 volts or 24 volts. On a cold morning, the battery may only put out about 10 volts, 10.5 volts or so. When the engine's being started, that might plummet to 8 or 7 volts. On the other hand, when the engine's running and the alternator is charging the battery, the voltages on a 12 volt electrical system might be in excess of 14 volts, sometimes close to 15 volts. And on a 24 volt power system, it can be about 28, 29 volts or so. So we need a system that also has the ability to tolerate a wide range of voltage inputs and anything that fluctuates in between. Our system is designed to take 7 volt DC all the way up to 36 volt DC and function with any voltage that fluctuates in between that range. And that allows us to actually take power off of a vehicular power grid and run it to our system and operate reliably in that environment. In addition to that, in addition to the voltage range, it is also very important that we are ignition aware, because when the vehicle is started, you cannot realistically expect the driver of the vehicle to go turn on the system, and more importantly, when the vehicle is parked and the key is turned off and the driver walks away, it's very difficult to tell the operator of the vehicle to say, oh, you can't turn off the vehicle, you have to go turn off the system, you have to shut it down gracefully before you turn off the vehicle so you don't corrupt the application or cause the operating system to crash over time. So that has to be automatic. So in addition to the wide voltage range, we have built in the ability to have an ignition aware power management system. What it does is that it senses the state of the ignition. When the vehicle is turned on or turned to the accessory on position, the system powers itself on automatically. Now, what's more important is that when the vehicle is turned off, because the system doesn't just lose power immediately, it continues to draw power from the battery, while it detects and knows that the ignition has gone from high to low. It waits a predetermined programmable delay, and then it issues a soft shutdown command to the operating system. If you're in the Windows operating system, you will see the operating system come up with a message saying that Windows is shutting down. It will quit the application sequentially and then go into standby mode. Once that has transpired, after a second programmable delay, which is normally set to, let's say, 3 or 5 minutes, then the system will cut power. That way, we avoid hard, unexpected shutoffs, and you don't get operating system or application corruption. As additional safety to the system, if you ever hook up the ground and the battery terminals in the opposite direction, if you put a battery to ground, ground to battery, the system is designed with reverse voltage protection, so that wouldn't hurt it. It can also take surges of up to 80 volts, and it will not be hurt by that either. Once the system is actually shut down, it actually goes into standby mode. Now, it doesn't draw a lot of power in that state. It draws less than half a watt. However, over time, that still drains charge from the battery system. So we also have a battery guard that monitors the battery state, and if it goes below a certain voltage, it actually cuts the power to the system completely. In that state, when the vehicle is started, the system actually will not come on automatically, but at least the vehicle will be able to be started. In addition to that, just to make it operate not just well, but very robustly in a vehicular environment, this system is designed to be 100% solid state. There is no moving parts. There is no fans. Storage is 100% NAND flash solid state disk. The cooling is 100% passive, and the entire system is made from either an aluminum extrusion and thick 1.5mm aluminum plating. That ensures that when mounted, the system is actually very, very resistant to vibration and shock. Now, after we have made sure that the system can survive temperatures and voltage conditions and the operating environment of vehicles, we also have to make it easy for these systems to actually function in the intended role, which is to deliver digital content to either LED or LCD displays. So there are two aspects of that that I believe is worth addressing. The first is that the system, it can be remotely managed. It features Intel's active management technology. It has the ability to have not just terrestrial, copper, gigabit Ethernet connections, but also Wi-Fi and Bluetooth connections. If it's desired, it can also have a 3G or LTE wireless adapter internally, so that it can be communicated to via the cellular network. Sometimes, depending on the application, when you have a digital display or a public display on a bus, for instance, a shuttle bus, sometimes it's important to have certain information about the location of that vehicle or the state at which the vehicle is operating in. For instance, if you have an airport shuttle, it will be very, very useful to be able to have a location-based content delivery system, whereby if you arrive at Terminal 3, the vehicle knows that it's at Terminal 3 and can display the relevant information and content. We're able to do that by having an optional GPS receiver that you can install in that system. It can also get data off of the vehicle's CAN bus system, so that it knows actually how fast the vehicle is going, for instance. It can probably also pull information like the engine RPMs and things like that, even though usually for digital signage that's not used as much. The system also has the ability to take adapters that allow it to have general purpose digital input-output interfaces. This might be useful, for instance, to trigger a relay that, for instance, open a little door or turn on a little light, showing that, hey, it's time to get off the bus, and it lights the way, and things like that. So those features are optional, but they can be added to the system. Now, there's one additional feature that we have in this system. In fact, it's a feature that we're proud of and that we have integrated into every single one of our digital signage product that came out in 2015 or later, and that is EDID emulation. Now, electronic display ID is a feature that you will find in DVI and HDMI connections. What it does is that it allows the video output port, an HDMI port, DVI port, to detect that there's a monitor being connected to that port, and also specifics about that display, what the native resolution is, what the refresh rate is, what other resolutions are supported by that display. Okay, and that's very, very nice. But it actually causes a lot of problems in digital signage. Now, if you have a laptop computer, you're probably quite familiar with what happens when you take a laptop computer into, let's say, a conference room and you plug that laptop computer into a projector. The first thing that happens is that the operating system, the driver software, the video controller, knows that a display has been connected. You get a little dialog box that pops up. The resolution changes. Now you can either have that projector to be a clone of your screen, or you can set it to be a second display, for instance. The same thing happens when you take a computer home and you plug it into, let's say, one or two external monitors, or when you hook an additional monitor out to your desktop computer. That's all very convenient, but in digital signage, that can be problematic. Imagine this. If you have a fast food restaurant and you have a digital signage player or system, and it's hooked up to 2, 3, or 4 TV screens that display the menu board. Now, somewhere along the way, when the system powers up, sometimes one of the screens do not come up as quickly, and that is detected as a change in display configuration. Or maybe somebody just unplugged the screen. Maybe one of the screens went down because it broke. That all constitutes a change in display configuration. Now, at a fast food restaurant, when one screen goes down, you have a black screen, that's bad enough. What you definitely do not want is for the remaining screens to have a little dialog box pop up or have the resolution change on those things. You want to lose one screen and have the remaining screens function as if nothing has happened. Traditionally, what happens is that professional installers will use something called an EDID emulation dongle. They plug these little dongles into a DVI port or an HDMI port to fake the EDID signal and fake the hot plug pin. It fools the system into thinking that a display is connected regardless of what happens to the display. You can unplug the cable, you can power down the display, you can break the display, and it really doesn't matter because the system is not aware of that. As long as the dongle is connected, the dongle is the display, and video signals will go out over that pin uninterrupted. Obviously, the dongle solves the problem of somebody, kicking a cable and displays going down. Dongles, however, do not solve the problem of the dongle itself falling out. Dongles also add, a bunch of paraphernalia in the back of the system which you have to deal with. So what we have done is we have taken the EDID emulation feature and we have built it on the logic board itself. Now, it's a feature that can be turned off, and it can be reset. But if you do not do that, once you have hooked up a display and it detects and stores the EDID values, you can disconnect the display, you could power down the display, and the system will not know it. The other display will not be affected. And this is a feature that you will find in all of our digital signage players, including this extreme environment player that we are talking about. So there are actually two versions of this product. The SE-92 is the first version, and this is designed for terrestrial, deployments. It does not have the vehicular power control system, but what it does have is the automatic on-off scheduler, which allows it to be programmed to come on at a certain time and go off at a certain time, and different on-off times for different days of the week, and so on and so forth. Now, this is called the SE-92, and that's the first version of this player. The second version is called the SE-602, and this is the vehicular-enabled version of the system. Physically, they are identical, but the firmware on both is different. In this particular case, in the case of this SE-602, we have a vehicular power management system. And what that does is that it allows you to take not just a wide range of voltage inputs, but also to be aware of the state of the ignition, to do automatic startup, graceful shutdowns based on the state of the ignition of the vehicle. Okay, so both of these systems will have the wide range voltage input. Both of them will have a wide operating temperature range. They have the same expansion capabilities. They have the same low wattage processors, and they have the same EDID emulation function. They have the same expandability. The difference is that there is a choice between whether you want an automatic power scheduler or a vehicular power management system in the firmware. And that's what defines the difference between the SE-92, the terrestrial version, and the SE-602, which is the vehicular version of this system. Thank you.